So, in this session we will be discussing about the stability of a system, and without the detailed analysis what will be the criteria of the stability and how it can be simplified into some elementary calculations. So, the topic is stability analysis. See, there are different, first we have to fix about the or talk about the criteria of the stability. So, if it is a system which produces a bounded response or bounded output in relation to a bounded input, then the respective criteria we refer as bounded input, bounded output criteria of stability. That means, if a system produces bounded output when a bounded input is given to the system, then the system is considered to be stable, right. So, this is called Bibo criteria of stability. There are other criteria as well, like this Lyapunov criteria of stability, that is also used in control, but here in undergrad we will not discuss it. Now, what is a bounded input, right, or bounded output? What is bounded? Input or output? When Ft is finite for all values of t, right. So, step, pulse, sinusoid are bounded input function. Right? Whereas impulse and ramp are unbounded, as it is obvious, because the ramp grows to infinity and impulse, this impulse function also momentarily grows to infinity and again drops to 0, right. So, this is the bounded input, bounded output stability criteria. Now, the point is, we cannot go on exploring the what will be the exact response of the system, because then we have to give a step input, we have to go for the Laplace transform, or transfer function must be multiplied with the a by s, then we go for Laplace, tedious Laplace inverse transform, then you generate the time domain function, and finally from there you conclude that whether the system is bounded or unbounded, right. But that's the first principle, procedure based on this first principle, that is a Bibo. Here we will try to simplify this condition for a system to be stable according to Bibo criteria. So, what is that? what is the condition for the transfer function of the system to satisfy Bibo criteria, that we are going to discuss. Right. So, here we will try to go by these examples, right, and then we will generalize that example. And what is the example? It is a general example as well. Let we have the transfer function GS, which is, we can split into numerator function and denominator function. Now, as we have studied in inverse response, the roots of ns equal to 0, that is z1, z2, z3, zn are referred as zeros of transfer function. And we have seen that these zeros are important for inverse response. Right? On the other hand, the roots of this denominator polynomial ds equal to 0, the roots of ds equal to 0, that is p1, p2, pm, or let us say this is m, this is n, right, or let us use small casing, are called poles of the transfer function. And this we will see, they are important for determining the stability. Right. So, how they are important and what is the logic, that we will try to understand and establish through considering a general transfer function. Let us say the poles are something like this. Let GS be ns by s minus p1, s minus p2, s minus p3 to the power m, s minus p4, s minus p4 star, and yeah, that's all. Where p1 and p2 are real single poles, p3 is real multiple poles, p4 and p4 star are complex conjugate poles. So, we have considered different types of poles to be existing in the transfer function, right. So, all the different types we have considered. So, y bar s is this ns divided by s minus p1, s minus p2, P3 to the power m, P4, P4 star into, let's say, A by S. A step input we are giving. So you have to get principally the inverse Laplace transform, that is a time domain response. So y prime t or y prime bar s for the time being, we have to break it into partial fractions. So C1 s minus P1, C2 s minus P2 plus C31 s minus P3, C32 s minus P3 square, C3m s minus P3 to the power m plus C4 s minus P4, C4 star s minus P4 star plus C5 by S. So if I take the inverse Laplace transform, I am not going to find out the values of C1 or all the constants, because transfer functions what we have considered is a general one, right? Unless the value or the expression of ns are given, we cannot actually calculate. So this is a demonstrative kind of example, right, where we will try to understand the role of these poles in the stability of the system. So y prime t is C1 e to the power P1t, then C2 into e to the power P2t plus C31, C32 into t, C33 t square by factorial 2, C3m t to the power m minus 1 by m minus 1 factorial into e to the power P3t. Then plus C4. Now you see, let P4 and P4 star be alpha plus minus j beta, where j is under root of minus 1. They are complex conjugate. So C4 into e to the power alpha plus j beta t plus C4 star into e to the power alpha minus j beta t plus C5. Now let's focus on this or these terms. So first we'll try to understand that how the term C1 e to the power P1t or C2 into e to the power P2t affect the stability. Now you see, if I plot this type of exponential function C1 into e to the power P1t, let's versus t, we are plotting it. So it will simply grow to infinity for P1 greater than 0. And only because of this term the system becomes unstable according to Bibo criteria. Next, if P1 is negative, then it will decay to 0. Right. So for the term C1 into e to the power P1t, the system will not be unstable. Right. It may be unstable because of the contribution of other terms as well. But if we consider the response of this first pole, which is real, positive and single, Because of the contribution of that specific pole, the response is not going to be unstable. So, conclusion is, for stability, the poles, real and single, only for that we have concluded, must be negative. Next, multiple poles. The term, the expression is C31, C32 t by factorial 1 up to C3m m minus 1 factorial into t to the power m minus 1 into e to the power p3t. Let this be capital Xt. Let. Now, capital Xt decays to 0 as p3 is negative and grows to infinity if p3 is positive, because the exponential term in the product function will dominate the overall trend of this function, right. The polynomial will not be that much influential or powerful to dominate this entire, because exponentially, as you know, it's an infinite series of polynomial, right. So, inference same as real single pole is valid, is also valid here. Right? Next we will think about the complex conjugate poles. Now, complex conjugate poles, you see, we have already got the time domain response as e to the power alpha plus j beta whole bracket t plus some constant into e to the power alpha minus j beta whole bracket t. Right. Now, you see the term let yt, capital Y, is the C4 into e to the power alpha plus j beta t plus C4 star e to the power alpha minus j beta t. So, what we can do? We can simplify this as e to the power alpha t into C4. Now, e to the power j beta t. So, we use De Morgan's theorem and write this cos beta t plus j sin beta t plus C4 star cos beta t minus j sin beta t. So, from here we get the C4 plus C4 star cos beta t plus j C4 minus C4 star sin beta t, and we can write that as capital A, a new constant, cos beta t plus b sin beta t. So, consider this r as b as r cos this phi and a as r sin phi. As you all know, it's a school level technique that r will be under root of a square plus b square, and this is phi. Phi will be equal to tan inverse of a by b. So we get e to the power alpha t into r into sine of beta t plus phi. Right. Now what will happen to this term? This is definitely a periodic term, but its magnitude is either progressively it will increase or decrease. And how to draw the profile of this sort of product function where a trigonometric oscillating function is coupled with this exponential function. The thing is, capital Y here, first let us consider alpha greater than 0, right, alpha positive. Then draw this e to the power alpha t profile and take the mirror image of that about the t axis. This will serve as an envelope for this sine function. So it will be like this. So it will be growing and growing, it will grow to infinity. So alpha greater than 0, yt grows to infinity. Whereas the same is true, this envelope issue, that we draw the envelope for alpha less than 0, we plot y, and we will see that the amplitude is decreasing progressively. So yt decays to 0 for alpha less than 0. And what is alpha? Alpha is the real part of the pole. So what will be our general conclusion? So we have explored the real, single, real multiple and the complex conjugate. And the conclusion is that for stability, the real part of all the poles must be negative, right. So that we derive from this baseline criteria of Bibo. So let us first summarize it, what we have got, and after that we will proceed with that. So stability Bibo criteria, all the poles of the transfer function must have negative real parts. That is, if I draw an organ plane, this is the region of stability. The location of poles for a system to be stable. Right. So that's the outcome of this Bibo criteria. Now you see why we are interested so much about the stability. Because stability has a direct connection with the design of a controller. Right. Because say a system originally it is stable and you have connected it with a feedback loop and attached a specific controller and tuned the controller with the specific value of its parameter, and it may happen that the overall response becomes unstable, right. And similarly, this is the negative side of this issue, but similarly you can stabilize an unstable system. So when we design a controller, mostly feedback, we must ensure the stability of the response. right? Definitely we have to ensure the stability. So, our first example, see, a system is let us say it is 10 divided by s minus 1 into m prime plus 5 divided by s minus 1 into d prime. That is the open loop response. So, P1 or P is equal to 1 and it is an unstable system, that we can understand. Now, attach a control loop with P controller, and we consider, as we did in case of simple feedback loop dynamics, then GM and GF we consider to be equal to 1. So, now Y prime P controller means GC equal to KC. Now, Y prime, it is basically what? This GC, GF, GP. GC is KC, GF 1, GP is 10 divided by S minus 1. Denominator 1 plus KC into 10, 1, S minus 1 into 1 into this YSP prime plus GD. GD is 5 divided by S minus 1, denominator remains same, KC into 1 into 10 divided by S minus 1 into 1, D prime 1. Now, you see what happens, 10 KC divided by S minus 1 plus 10 KC into YSP prime plus 5 divided by this S minus 1 minus 10 Kc into D prime. So, essentially we can restructure it as S minus 1 minus 10 Kc into YSP prime plus 5 divided by S minus 1 minus 10 Kc into D prime bar. Now, if we make it positive, right, then the poles becomes negative. This quantity, if I make it negative, sorry, this is negative. So, 1 minus 10 Kc negative. So, 1 divided by 10 less than Kc. So, Kc greater than 1 by 10, it will yield stable response, because the pole is now positive, it is negative, right. For Kc greater than 1 by 10, the respective pole, which was previously for this open loop system, was equal to 1, right, and hence unstable. Now, it will be stabilized upon attaching a feedback loop. So, this is a positive kind of example which is desirable, that we have to go for designing a feedback controller which will convert an unstable open loop system into a stable closed loop system. Now, just the alternative one. Let us think of a stable system, right. Let us think of a stable system. Gp is equal to 1 divided by s square plus 2s plus 2. It is a second order, right. And if we find the roots, P1 and P2 will be minus 1 plus minus j. So, this real part is negative, so hence stable. Now, we attach Pi controller. So, Kc into 1 plus 1 by tau is, right, and GMGF again equal to 1. And let us consider only the servo mode. So, Y prime here, if we resolve it, will become Kc into 1 plus tau is by tau is divided by s cube plus 2s square plus 2 plus Kc whole bracket s plus Kc by tau I into YSP prime bar. Now you see, if I choose a value, if we set Kc equal to 100 and tau I equal to 1, then the roots, what are the roots? What are the poles rather? P1 is minus 7.185, negative, so fine. But P2 and P3 are 2.59 plus minus 11.5 J. Right. So what we observe that this is positive. So it will become unstable. So originally it was a stable system, and we have, say, this is a typical example of designing a wrong type or choosing a wrong type of controller parameters, that is a wrong tuning, and we have got an overall system becoming unstable. Right. So that's the two typical cases we have discussed. In the first case, we have stabilized that originally open loop unstable system, and second case, we have destabilized an originally stable system by the wrong choice of these controller parameters. Right. So what we note that upon attaching a feedback loop, a system may be stable or may be unstable. So, and that entirely depends on the values of the controller parameter. So, controller parameter, it's a crucial in determining the stability of the loop, and as this feedback loop and associated response is quite important in chemical process industry, because everywhere we have to attach this sort of loop, we must focus more deeply into this characteristic or into this specific stability issue of this feedback loop. Right. Now, for a feedback loop or a feedback control system, we have y prime is equal to Gc Gf Gp divided by 1 plus GOL into YSP prime bar plus GD divided by 1 plus GOL into D prime bar. So you see both the denominators which will determine the sign of the roots, right, whether it is positive, negative, or rather the real part whether it is positive or negative. It's basically this expression 1 plus GOL. So the roots of 1 plus GOL equal to 0 is important, or they will dictate the stability of this entire system, and that is called the characteristic equation. This is the characteristic equation of the feedback loop. Now, roots of this characteristic equation determines the stability of a system. Right? So, everywhere what we will do. Previously, I have stated the example, and there the characteristic equation which is appearing in the denominator is a cubic equation, and it's not easy to solve a cubic equation. It may be an equation with order greater than a polynomial with order greater than 3, right? Then we have to go by numerical techniques, and the complex root, if it appears, then it is further complicated. So, we have to keep in mind that we don't want the exact values of the poles or the roots of this characteristic equation, right? Rather, we should call it roots. They are not poles. It's not exactly a transfer function of a system, but rather the transfer function of the entire feedback loop, right? But for the roots of the characteristic equation, we don't have to solve. We only have to know about the sign of this real part of the respective roots, right? And from there we can conclude about the stability. So, there is something called Descartes' rule of sign, where taking the sign of the coefficients actually we can conclude about the sign of the respective roots. So, that has been implemented in process control and gave a foolproof criteria without such that without solving this equation we can conclude by simple analysis we can conclude about the sign of the poles, and that is called the Routh-Hurwitz criteria, right. So, you are going to study now the Routh-Hurwitz criteria, which will give you an easy way to determine the sign of the real part of these roots of this characteristic equation without actually solving it. So, Routh-Hurwitz criteria, it comprises of two sequential tests. What is that? Let 1 plus GOL equal to 0, let us write it as A naught s to the power n, A1 s to the power n minus 1, finally An. You should write it in the specific format, it should not be confused with An s to the power n, otherwise you will get wrong results. So, you write this in this form. So, first it is test 1. Check whether all the coefficients are positive or all negative. If yes, then go for test 2. Otherwise, conclude the system to be unstable. Right. We can directly conclude the system is unstable because if any one of the root is negative, right, at least there will be only one pole with positive real part, and that will lead you to instability. Now, even if all the roots are positive, still we can have poles, or we can have roots with, all the coefficients are positive, all the coefficients even if they are positive, still we can find roots with negative real part, right. And to confirm that, we have to go for test 2. So, what is test 2? Construct Routh-Hurwitz stable. So, what is that? Row 1, A0, A2, A4, A6, etc. Row 2, A1, A3, A5, A7, etc. Row 3, capital A1, capital A2, capital A3, capital A4, etc. Now, what is capital A1? Capital A1, this is direct implementation of Descartes' rule of sign. Capital A1 is A1 into A2. No, let me check just. Yeah, A1 into A2 minus A0 into A3 divided by A1. So, this into this. Next, capital A2 is just sequential multiplication, A1 into A4, A0 into A5 by A1. A3 will be obviously A1 into A6 minus A0 into A7 divided by A1, and so on, right. So, in this way we should continue R4, B1, B2, B3 dot dot. So, what will be B1? Following the same rule, but with the previous two rows, that is capital A1 into A3 minus small a1 into capital A2 divided by capital A1. B2 will be equal to capital A1 into A5 minus small a1 into a3 divided by capital A1, and so on and so forth. So, in this way we will continue unless we get 0 here, right. All the elements of the row are 0, and there we will stop. Now, what is the Routh-Hurwitz test 2? Consider the elements of this Routh-Hurwitz table in the first column, right. And what is the conclusion? If any one of the first column element of Routh-Hurwitz table is negative, then the system is unstable, right. That means there is at least one root with positive real part. Okay. Moreover, here though it is not associated to stability, the number of sign change is same as the number of roots with positive real part. Like for example, if I get the first column as say 1, 2, minus 1, 3, minus 1, 2, 0. Then the number of sign change 1, then 2, then 3, then 4. Right. So 4 roots with positive real part. That we can conclude about the number of roots with positive real part, and definitely the system is unstable, right. So, that is basically the Routh-Hurwitz criteria of stability, and there is also another stability criteria or stability test that is called the root locus test, but this is beyond the scope of GET. So, we are not going to discuss it right now. If time permits, definitely we will come to that root locus. Okay. So, let us solve some of these or conclude about this stability for typical feedback loop, and therefrom let us determine what should be the favorable range of controller parameter to have a stable response. So, definitely it is the example is the beginning step regarding the design of the controller. So, what is the example? Let us see. Let us have a process (10 e to the power minus tau ds), right, divided by s plus 1, and the controller is P controller, GM GF equal to 1. Okay. Now, what is the characteristic equation? But before that, let us find out the open loop transfer function. So, 10 into e to the power minus tau ds divided by s plus 1 into Kc into 1 into 1. Now, with that we cannot work. So, we have to use here the Pad's approximation. So, let us use Pad's first order approximation. So, 1 minus tau d by 2 into s divided by 1 plus tau d by 2 into s. So, that is the open loop transfer function, and characteristic equation will be 1 plus 10 Kc 1 minus tau d by 2 into S divided by S plus 1 into 1 plus tau d by 2 into S, and that is equal to 0. So, this is S square plus this is tau d by 2 S square plus this S plus tau d by 2 into S plus 1 plus 10 Kc minus 5 Kc tau d into S. So, this is giving you tau d by 2, this is equal to 0, tau d by 2 S square plus 1 plus tau d by 2 minus 5 Kc tau d S plus 10 Kc equal to 0. So, you see here that we have to go for first test, right, and for a quadratic equation we do not have to actually go for the second test. Why? Because a quadratic equation is a0 s square plus a1 s plus a2, right. So, all this, let us say all these are positive. Now, what is the Routh-Horowitz table? a0, a2, a1, 0, 0, 0, right. What will be this element? a2 itself. So, what are the, and this is 0, 0, this will be further 0, 0. So, we have to stop here. So, what are the first column element? The coefficients itself. So, if I check the coefficients are positive, definitely that is same as checking the first column of the Routh-Horowitz test or Routh-Horowitz array to be positive. So, for quadratic characteristic equation, only the first criteria, first Routh-Horowitz criteria is sufficient. So, tau d by 2, the dead time, this tau d is definitely positive, Kc is definitely positive. So, we have to set this coefficient to be positive. So, 1 plus tau d by 2 minus 5 Kc tau d must be greater than 0. So, 1 plus tau d by 2 divided by 5 tau d, and Kc must be less than equal to this. So, this is the criteria of this controller design, right. So, Kc must vary between 0 to this specific expression, that is 1 plus tau d by 2 divided by 5 tau d. So, next you see that and we can check it, this is given in the example, that instead of using the pad's first approximation, if I use it as tau d square s square minus 6 tau ds plus 12 divided by tau d square s square plus 6 tau ds plus 12, the criteria finally will remain same. So, it is immaterial that what we are using, what sort of approximation we are using, whether it is the Routh-Horowitz or the pad's first approximation or pad's second order approximation. So, everywhere you will get the same result. So, let us solve another example which is also given in the handout. So, here Gp is equal to 1 divided by s square plus 2s plus 2, a second order system which is stable. Gm and Gf equal to 1, and we are using a PI controller, right. So, what is the transfer function? 1 plus GOL, characteristic equation. So, 1 plus GOL is 1 divided by s square plus 2s plus 2 into this Kc 1 plus tau is divided by tau is equal to 0. So, tau is cube plus 2 tau is square plus 2 tau is plus Kc 1 plus tau is equal to 0. So we get tau I s cube plus 2 tau I s square plus 2 tau I plus 2 kc tau I. Yeah, 2 kc tau I whole s plus kc equal to 0. Right? So if you simplify, it will be s cube plus 2s square plus here 2 1 plus 2 kc s plus kc by tau I equal to 0. Now all these coefficients, yeah, 2, this 2 will not be there. Just a minute. 2 plus kc. Now here there is no 2, so it is 2 plus kc. Yeah. So all the coefficients of this characteristic equation, it's positive. So you have to go for Routh-Hurwitz test 2. So this is A0, that is 1, A1, that is 2, A2, that is 2 plus kc, and A3, it's kc by tau I. So row 1 will be A0 and A2. So 1, 2 plus kc, 0, 0. Second row 2, then kc by tau I, 0, 0. Next, cross multiply this, subtract this, divide. So 2 into 2 plus kc minus kc by tau I divided by 2. Here this is 0, 0, 0. And for the third, this minus this divided by this. So it is kc by tau I, again 0, 0, 0. And here 0, 0. So which one we have to set the condition? Definitely on this one. Right, because there is a minus sign and this is expression. Kc tau I 1, 2, these are by definition positive. So 2 plus kc whole bracket 2, yeah, 2 plus kc whole bracket 2 minus kc by tau I must be positive. Right? Yeah. So if I group this, 4 plus kc 2 minus 1 by tau I. 4 plus kc 2 minus kc by tau I greater than 0. Or this, we can write this is a minus and this is plus, this is minus. So kc must be less than 4 divided by 1 by tau I minus 2. Right. So if I fix this tau I, definitely this is not a deterministic way of giving that these two are the values of kc and tau I, but this will give you a criteria. Right. This will give you a simple criteria. So if I fix tau I, definitely we will get a range of kc from 0 to this specific value. And alternatively, if I change this expression not for kc but rather for tau I will get kc, we can choose anything, but tau I, it must satisfy that respective greater than or less than expression of kc. Right. So that's all about the stability, and basically you see the stability will not give you the exact optimum value of this controller parameter. That is the domain of tuning, and there are different tuning techniques, criteria based on which we can exactly fix the values of this controller parameter like kc, tau I or maybe tau d. But here, whenever you are designing a controller, it's very, very important that you must first ensure the stability. Right. Even you think that okay, you have applied some empirical tuning technique which does not consider the stability criteria as its baseline condition. So in that case, even if you get a good controller design and it can control the process, but for some input the output blows to infinity and the output becomes unstable. So that must be taken care of. Whatever controller you design, you must check it that whether it is going to give you a stable response or not, right. Now, in the next session, we are going to start something called frequency response, and in frequency response, actually, the input will be a sinusoid, and we will see that for all systems, the stabilized output, that means, or which we should not say it's stabilized, it's sustained output. Initially, there will be some brief transients, right, but the sustained output will also be a sinusoid. And from this frequency response analysis, we can actually reveal some of the very important features of the transfer function, which we cannot actually decode using the standard monotonic input like step or pulse or ramp or impulse, right. So, that is why the frequency response analysis is very important. And you may be thinking that why we have to decode this transfer function. See, most of the process systems are highly complicated and non-ideal. So, there we have to determine its working transfer function through experiment, right, not by modeling. Like a distillation column, if I change the input or the flow rate or the reflux ratio or something else, how this distillate or composition or the bottom product composition is going to change, right, dynamically. So, it is not very easy to determine because there are always non-idealities associated to tray hydraulics, to vapor flow, to distribution of the liquid and vapor over the entire tray. So, we have to, definitely we will go by a model, but we have to cross check and verify that whether we have got the exactly accurate transfer function such that we can go for designing of a controller. So, there we have to conduct experiment with the prototype small scale model distillation column, and from there we can fix the transfer function. So, if I give some frequency response or this oscillating input, then we can reveal some of the hidden characteristics of this transfer function such that if two poles, say it is a multi-capacity first order, second order process, right, multi-capacity second order process, and the two poles of these transfer functions are very close to each other, okay. Two poles of the transfer functions are very close to each other. So, there what can happen that using this step input or this pulse input, we cannot actually differentiate about these two poles, but if I use a frequency response analysis, definitely with surety we can identify that these two are the poles, and even these can be resolved with a very low resolution of these poles which are very close to each other, maybe in the order of some decimal places, okay. So, that is the specific utility of frequency response analysis, and there are stability criteria based on this frequency response analysis which we will be discussing in the next session. Thank you.